Okay, so having established that magnetic induction is something that happens, that changing magnetic fields can cause electrical currents, we want to talk about the specific laws of physics that govern this process. So this is chapter 29 in your book. Your book actually starts out with a description of exactly what I just talked about in the video, which is that if you've got a coil of wire and you somehow cause a changing magnetic field in that coil, that induces a current in that loop, or an induced EMF, a source of electrical potential difference, and that causes electrical charges to flow through that loop. So let's take a look at how we actually define this process quantitatively. The first thing we have to do is we have to define a notion of magnetic flux. Just like we defined electric flux in the chapter on Gauss's law as sort of the amount of electric field passing through a surface, and we define that as the integral of E dot dA. The definition of magnetic flux is just the integral of B dot dA, where the magnetic field is passing through some loop enclosed by some enclosed loop in space, and A is the area of that loop. Usually when we're talking about magnetic induction, this loop actually physically represents some kind of wire, and we're talking about the induced EMF or the induced current in that wire. It doesn't have to be a physical wire. This can be an abstract loop in space, and we can define the magnetic flux through that loop. But the magnetic flux is defined as the integral of B over the surface area of the loop, with the understanding that the only flux that counts is the perpendicular flux, so the dot product between B and dA establishes that if you've got, for example, a magnetic field that's oriented this way, and you've got a loop that's oriented perpendicular to that, the flux is maximized. But if you've got a loop that's, say, oriented like so, the flux through that loop is zero, because the magnetic field is always parallel to the normal vector. Sorry, well, it's perpendicular to the normal vector to that loop. So let's look at how we use this definition of flux to determine what's called the induced EMF through a loop of current. This law, equation 29-2 in your book, is called Faraday's law. It says that the induced EMF through a loop in space is equal to the time rate of change of the magnetic flux, d phi sub b dt, with a negative sign in front. And that negative sign is very, very important, and we'll talk about it in a minute. We call this Faraday's law of induction, or simply Faraday's law. So according to Faraday's law, what causes an EMF is a change in magnetic flux through some closed loop in space, either real or imaginary. By the way, if it's a real loop and it's a loop that consists of wires, okay, making a physical loop, and those wires actually have multiple loops, so you've got like a coil of wire. If there are n coils in the wire, the total flux for that loop is n times the flux. So for multiple loop coils, Faraday's law looks like this. The EMF is equal to minus n number of loops times d phi dt, the rate of change of the magnetic flux. And this equation allows you to calculate numerically how much magnetic, or how much EMF is generated by a change in magnetic flux. But it also allows you to understand sort of conceptually what EMF is created in a particular situation, and how much and in what direction the induced EMF is. Your book gives a special section to something called Lenzs law. Lenzs law is just a qualitative statement of the meaning of the negative sign in Faraday's law. The negative sign in Faraday's law is very important. It's probably fair to say it's the most important negative sign in any physics equation. And it tells us this. It tells us that the direction of the induced EMF when there's a change in magnetic flux is such that it opposes the change in magnetic flux that created the EMF in the first place. So let's read the way your book states this. A current produced by an induced EMF moves in a direction so that its magnetic field opposes the original change in flux. This is known as Lenz's law. It rephrases it another way. An induced EMF is always in a direction that opposes the original change in flux that causes it. So if you're creating an EMF by decreasing the flux through a loop, the current induced in that loop will be in such a way to oppose that decrease. In other words, to try to keep the same amount of magnetic field pointing in the original direction. If you create a change in magnetic flux that increases the magnetic flux through the loop, the induced current in that loop will act in such a way to oppose that increase. So in some sense, the induced EMF is always fighting against the change that created it, and that difference in direction, that opposite direction, is embodied in that negative sign in Lenz's law. And we can talk about conceptually how the universe would be different if that negative sign was a positive sign instead. But for now, we just want to look at a bunch of examples of different situations where you generate a EMF by changing the magnetic flux, and just work through the process of figuring out the direction. There's lots of right-hand rule stuff going on in order to do that. So we look at these two equations together, the definition of flux and Faraday's law. If flux is equal to the integral of the magnetic field over some surface, okay, so you've got a loop in space, there's some magnetic field through that loop, the integral of B over that area A is equal to the magnetic flux. And the induced EMF around that loop is equal to the rate of change of that magnetic flux. We can see that there are three different ways to generate a change in magnetic flux. If the magnetic flux is equal to B dot dA, we can change the strength of the magnetic field. In other words, make the magnetic field through that loop stronger or weaker. We can change the area of the loop by making this loop of wire bigger or smaller, or adding or subtracting loops from that wire. Or we can change the angle between B and A such that the dot product between B and A changes from perpendicular to parallel, or any angle in between. So in the rest of the chapter, we'll see many examples of ways to generate a changing magnetic flux by changing either the strength of the magnetic field, the area of the loop, or the relationship in space between the magnetic field and the loop itself. So here's an example from the book. Imagine you've got a loop of wire that looks like this. You take a magnet and you push the magnet into the loop this way. Okay, so the hand is moving upward, increasing the magnetic flux in the positive Y in the upward direction. What will the direction of the current be in that loop? So you're moving the magnet up, it's creating a magnetic field upwards, and it's increasing the flux through that loop. Lenz's law and Faraday's law say that the induced current in that loop will act to oppose that increase in flux by creating its own magnetic field that fights against that increase. So the magnetic field of the loop, when current is flowing through it, is going to be pointing in the downward direction, which means by the right-hand rule, the direction of its current will be around this way. So, and that's the way that your book has it drawn. The direction of the current will be around the loop in that direction. That's the direction of the current that creates a magnetic field that opposes that increase of flux. Suppose you were holding this magnet in the loop and pulled it away, removing it from the loop. That has the effect of decreasing the magnetic flux through the loop. The direction of the magnetic field through the loop is this direction, but you are decreasing it from big to small as you pull the magnet out of the loop. That creates a change in flux, a decrease in the magnetic flux in the upward direction, and the induced current in that loop is going to want to fight against that decrease. The way it fights against that decrease is by creating its own magnetic field in the upward direction. Okay? The magnetic field is pointing up but decreasing. So the current that opposes that decrease, that opposes that change in flux, is a current that has its magnetic field in the upward direction. And by the right-hand rule, that is a current that wraps around the loop this way, which is what your book has drawn. Yeah, it's not a very good arrow. Let me do that again. Wraps around the loop. Use a big marker. Wraps around the loop this way. Okay, so that the magnetic field of that loop by the right-hand rule points in the upward direction. Okay? If we look at this example in the book, you've got a loop of wire, it's actually multiple loops of wire, in a circular shape, in a magnetic field that points into the page or into the screen. And you take that loop and you stretch it this way. What induced current will there be in the loop? The magnetic field is constant, but the flux is equal to the integral of B dot dA through the surface of that loop, and what you're changing is the area. You're changing the area of this loop by stretching it. You're making the area smaller. Okay. So the flux in the into the board direction through this loop is decreasing. Okay. If the flux is decreasing in the into the screen direction, the EMF induced in that loop is going to want to fight against that decrease. You fight against the decrease by creating your own magnetic field in that same direction, okay, into the paper, into the screen. And the direction of current that creates a magnetic field into the screen by the right-hand rule is a current that goes around the loop this way. Okay, so there will be a current in the clockwise direction around that loop while it is being stretched. Once you stop stretching it and hold it still, the current will stop, okay, because there's no change in flux. If you squish it again, the current will flow in the opposite direction because you're then increasing the flux, and you're going to fight against that increase by opposing that magnetic field. The next thing your book does, on example 29-4, is just a bunch of situations with magnetic fields, changing fluxes and changing magnetic fields through all the different ways you can imagine creating that change in magnetic flux. So here's example A. You've got a magnetic field and a loop of wire, and you pull the loop out of the magnetic field. Example B, you've got a magnetic field and a loop of wire, and you shrink that loop and you make it smaller. Example C, you've got a loop of wire and a magnetic south pole coming out of the page through that loop of wire. D, you've got a loop of wire and you've got a magnetic north pole moving in the plane of the paper towards that loop. And lastly, a loop of wire with a magnetic field pointing towards the left, and the loop of wire is vertical and you're rotating it this way. And the example asks you to think about, for each of these situations, A, B, C, D, and E, what will the direction of the current be in that loop? So do that now yourself. Think about the answer to those 5 examples, and I'll record a separate video where we actually go over the answers to that, and then we'll do some actual quantitative problems looking at how to calculate the EMF through one of these loops.